Cool. Hello to those of you who are watching this recorded. Okay, so what questions do we have? I believe this midterm is on everything from determinants all the way through stochastic matrices. So, someone has to go over diagonalization, so we can go ahead and talk about that. Before we do that, I'm just going to talk about inverse matrices just so we can build up to that. So, inverse. Okay. So, um, just to talk about some ideas of inverse matrices and how we know they're invertible. Inverse matrices, the following statements are all the same, okay? So how you check, the easiest way to check, if the determinant is not equal to 0, then invertible, okay? Simple as that. Another little like sidebar here, as we like go forward, just as a sidebar, the determinant of matrix A is the same thing as the product of eigenvalues, okay? That's just a little side note. So if you know you have 0 as a eigenvalue, you know your determinant also has to be 0, because whatever your other eigenvalues are, when you multiply them all together, there's still a 0 in there, and your determinant ultimately becomes 0. So saying that your determinant is equal to 0 is the same thing as saying that you know you have an eigenvalue of 0. Or rather, if you know you don't have an eigenvalue of lambda equals 0, you know the matrix is invertible, okay? They always have to be square for the sake of this class. N by n, I'll call it. They always have to be 1 to 1. They always have to be onto, okay? True for invertible matrices. They are always, n by n, they are always 1 to 1, they are always onto. Saying a square matrix is onto, you know there's a pivot in every row, if there's a pivot in every row, then you know that it's also invertible because it's also 1 to 1. Okay. Questions about this stuff so far? This is just how to determine if a matrix is invertible. The factor expansion of the candidates polynomial. Okay, yeah. Well, I'm leading up with invertibility to talk about diagonalization, and then we'll like talk about why they're a little different. Okay. Cool. So that's the basic of invertible matrices. The whole point is that we have AX equals B. Okay. And if you're given an invertible A and you're given some B, the whole point of having an invertible matrix is so that you can find X, so that it is A inverse times B. That's the whole point. Okay, that's like the idea and the motivation behind it, is so you can go backwards. You can go from B to X. Cool. Yeah. And now we'll talk about some diagonalization. Okay. Well, actually, just on the note of invertibility, the way to find it for anything bigger than 2 by 2 is you have your matrix A and you augment it with the identity of the same size. Okay. So if you have something that looks like this, no, 0, 0, 1, we augment, this is your A here, okay? To find the inverse, we augment it with the identity, and then we row reduce it so that the left side becomes the identity. Okay, and then on the right side of the augment, we're going to have A inverse, whatever that is. So for a 2 by 2 case, it's a little easier. Inverse is equal to 1 over the determinant. I believe it's D, negative B, negative C, A. Yeah. I always get them mixed up which one is flipped and which one's negative. So yeah, okay. Just wanted to make sure I wasn't saying anything incorrect or out of pocket there. Okay, cool. That's how we generally find an inverse. You guys shouldn't be expected to find the inverse of a 4 by 4 or anything incredibly hard. Okay. Um, yeah. So that's inverse. Now I have diagonalization. Okay. So this has to do with eigenvalues and eigenvectors. All right. All right. So the whole idea is find our lambdas and eigenvectors. And from here, put them in matrices. Okay, that's essentially the whole idea behind diagonalization. All right. So the way that it looks is C. Well, we'll start with D because D is a little easier. D stands for diagonal. D equals, here you have lambda 1, lambda 2, all the way to lambda n, whatever they are, okay? Having 0 everywhere else, okay? For C, extremely similar. Have V1 corresponding to the same column, okay? V2 corresponding to the same column that lambda 2 is in, all the way to the n, okay? One important to note is it is not going to be diagonalizable if we can't fill this matrix, okay? If we don't have enough VNs or enough eigenvectors so that we can fill this matrix, it is not diagonalizable. That's the whole idea. So that goes to say this whole thing boils down to for a matrix to be diagonalizable, all algebraic multiplicities must be equal to the geometric multiplicity of that eigenspace. Okay. So that's essentially what this boils down to, okay? For every single eigenvalue, regardless of how many times it's repeated, you have to be able to construct a matrix that has the same amount of eigenvectors. Okay. Yeah. Okay. This is the idea and the motivation behind all of this. So with a pretty basic example, this matrix here, okay, we can talk about, first of all, is it invertible? Yes or no? You don't have to tell me the inverse if there is, but okay, it is. Why do we know it's invertible right off the bat? Feel free to unmute yourselves as well. That's fine.
The determinant isn't 0.
Yep. Yes. The determinant not equal 0. Simple as that. If you have a matrix and they ask you if it's invertible, if it's easy to find the determinant. If it's not 0, it is. If it is not 0, it is invertible. Okay? If it is 0, it is not invertible. Okay? We don't want it to be 0. All right. Now, is it diagonalizable? Okay. Okay. Might not be as easy off the bat, but we know it's upper triangular, right? So for any upper triangular matrix, that's essentially where I can like draw a line to the diagonal, and then everything else is all of my numbers that aren't 0. Okay. If it's diagonal, or if it's triangular, we just know our eigenvalues are lambda equals 1 and lambda equals 1, right? So that's the same thing as saying 1 with a multiplicity of 2, okay? And that's an algebraic multiplicity because it's a number, okay? A number can't have a geometric multiplicity because that doesn't really make sense, right? Geometric things are shapes, you know? A vector is geometric, so it has that that like part to it. That's how you can kind of remember it. So the actual value itself has whenever I say like 1 multiplicity of 2, that is an implied algebraic multiplicity. Okay, so now, okay, the trick is how do we find the eigenvectors, and are there, for this case, this has a multiplicity of 2, so we need to find 2 eigenvectors that are linearly independent that correspond to this. Okay, there's a couple of different ways we can do it. So an eigenvector, no, what? I know this is a rather simple case, but I'm just trying to do something pretty basic and then we can expand on it. And if there are particular questions from the practice midterm, we can do an example from that as well. It's by definition the null space of A minus lambda I, right? Cool. That goes to say that it's A minus lambda I and multiply it by some vector gives us 0, right? That's the whole appeal of it. So that's what we have to do. This is also why we want there, for an eigenvector to exist, we have to have this. We have to have a null space, right? Because otherwise this whole equation can't happen. There's no way to get here if there's not a null space for that particular A minus lambda I, okay? So if there is a null space off the bat, it's just AV equals 0, okay? So that corresponds to the 0 null eigenspace is just your null space. Okay, just a little sidebar about that. Okay, so from here, an easy way that I like to think about this that makes life kind of easy, number of free variables in A minus lambda I is equal to your multiplicity, or also your geometric multiplicity. Okay, because that is the same thing as saying the dimension of the null space of A minus lambda I, right? And we're just composing it of the eigenvectors for an eigenspace, okay? Eigenspace is essentially boils down to just a null space of A minus lambda I. That is actually exactly what it is. Does this make sense? Does anybody have any questions on this? And this is the easiest way to like find out what the multiplicity is, okay? If you're really feeling it, you can take A minus lambda I, figure out the whole null space, put it in parametric vector form, take those vectors, those are your null vectors as well, or your eigenvectors, okay? This is just me trying to show that you don't have to necessarily find all the eigenvectors to know if it's diagonalizable or not, okay? So this is like the check, if yes, okay? So if geometric multiplicity equals algebraic multiplicity, I should say for all lambda, then A is diagonalizable, all right? Okay.
Get the multiplicity of like adding 1 and 1 from the matrix. Is that
Say that again?
to get 2? The multiplicity of you said you got it's 2. Did you get that by adding 1 and
1? Not adding, just because 1 happens twice on the diagonal here.
Oh, okay.
Okay, so that's why I say the eigenvalues are 1 and 1, because I want this to be this one, and this second one is this second one. So that's why it's 1 and 1. Or we don't want to say the eigenvalues are 1 and 1, so we just say it's 1 with a multiplicity of 2. Okay?
Okay, thank you.
Yeah. Cool. Yes. This is a big, important thing, okay? Cool. So going back, knowing all this information to this matrix, okay? 1, 1, 0, 1. We know we have lambda equals 1, multiplicity of 2. And we know our one eigenspace has, and then we're going to leave that blank for right now. So our one eigenspace is just the eigenspace corresponding to lambda equals 1, or the dimensional, the space that the eigenvectors span. That's essentially the idea, okay? So here, what do we want the dimension of the one eigenspace to be equal to if we want it to be diagonalizable? Or essentially how many, go ahead.
Is it 2?
Yeah, it's 2, right? Because of this part right here. Multiplicity of 2, we want to have 2 eigenvectors. Once. Okay? That's what we want. If we don't have that, it's not diagonalizable. Okay? Easiest way to check is we take a minus lambda I, okay, which in this case is 1, 1, 0, 1, minus this lambda, which is 1. So it's called plus, and I'll factor that in, okay? So this is obviously equal to 0, 1, 0, 0. And how many free variables does this have? Just the 1, right? Just one free variable here. One free variable, thus one eigenvector for lambda equals 1. Eigenspace has, or rather, a one, okay? And therefore, since this number and this number are not the same, we're done. We know it's not diagonalizable, okay? Does that process make sense? Does anybody have any questions about that? FV means free variables, yeah. Thank you for answering that in the chat.
So the geometric multiplicity, that's just the number of eigenvectors?
The yes, for that respective eigenvalue. Yep.
Okay.
Or technically linear independent eigenvectors, okay? Because technically, like for this, right, our eigenvector would be v equals like 1, 0, but it could also be 4, 0, right? Because it's just a vector in the null space, okay? And because I can say I have 2 does not mean I have a geometric multiplicity of 2, because there's only one like set of linearly independent vectors, okay?
Okay, thank you.
Cool. Any other questions on this?
Since we know that the determinant, like originally, is not equal to 0, does that mean it's not diagonalizable, like without having to do all of this?
No, it does not. Because what if I give you the matrix 1, 0, 0, 1? Okay, what's its determinant?
The determinant would be
1, right? So it is invertible, okay? And we're going to take a minus lambda I, exact same case, because it is technically upper triangular, or we can just call it a diagonal matrix because it's the same thing for this. Lambda equals 1, multiplicity of 2. I'm going to take a minus lambda I. We get the 0 matrix. And we can just say that this has our vectors of 1, 0, and 0, 1, right? So this has right multiplicity of 2, and a geometric multiplicity of 2. This is like the easiest example because it's the identity, but this works for everything, okay? In this case, something is invertible and diagonalizable. In this case, something is, it is invertible but not diagonalizable. We can also have something that is not invertible but is diagonalizable, okay?
All right, that makes sense. Thank you.
Cool, yeah, absolutely. An example of that third case where it is not invertible but it is diagonalizable. If I gave you the matrix 1, 0, 0, 1, nope, 0, okay? What is our determinant? It's obviously equal to 0, so it's not invertible. Okay, what are our lambdas in this case? You can still think of it as diagonal. We'll call it 1 and 0. Another fact that is super, super important and you should definitely remember for this exam, for each distinct eigenvalue, okay, there is at least one eigenvector, okay? Okay, so if you have lambda equals 4, lambda equals 3, and lambda equals -2 in a 3 by 3 matrix, you know automatically it is also diagonalizable because you have 3 distinct lambdas, okay? You know each one has to have at least one eigenvector, okay? Every lambda has to have at least one eigenvector. So if you have 3 eigenvalues that are different, you know each one has their own eigenvector, and you have 3 eigenvectors from that, right? So then you can construct your D matrix with your eigenvalues on the diagonal. You can construct your C matrix based on whatever eigenvectors those correspond to, okay? Cool. So in this case, this applies to this matrix as well. We have 2 distinct eigenvalues. Therefore, we have 2 eigenvectors. Therefore, for lambda equals 1, there's an algebraic multiplicity of 1 and a geometric multiplicity of 1. No eigenvalue. I'll write this down here as well. Nope, geometric. This is a big one, okay? No eigenvalue can have a geometric multiplicity of 0, so it must be at least 1. Always, 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 always. And it can be at most equal to the algebraic multiplicity, okay? These are the quick little like tips and tricks to get you through that really easily and really quickly, okay? So going back here, we have lambda equals 1 and lambda equals 0. We know each of them has at least one eigenvector, okay? So we can fill our C matrix with whatever V1 is and V2, so we know it fills, and that's basically the check to make sure that it is diagonalizable, okay? Therefore, it is diagonalizable. Cool. Questions on this one? Or anything about this or these important points down here? These will save a lot of time if you know how to use them. If they give you a question where it's like, here's the characteristic polynomial of a 4 by 4 matrix, and it says like, from that you can determine your eigenvalues, and you find that there's like an eigenvalue of 0, eigenvalue of 1, eigenvalue of 2, eigenvalue of 3. You know there's an eigenvalue of 0, so you know it's not invertible. You know you have 4 distinct eigenvalues, okay? None of them have an algebraic multiplicity of 2 or anything greater than 1, so you know it's diagonalizable as well. Okay. Could you give the answer as neither invertible or diagonalizable? Yes. Let me think about that for a second. Somebody asked, what is the difference between algebraic and geometric multiplicity? Algebraic multiplicity is how many times the lambda occurs in the characteristic polynomial. Okay, so if you have lambda minus 1 squared, you have lambda equals 1 happening twice, or with an algebraic multiplicity of 2 because of that square. Okay, geometric multiplicity is the geometric multiplicity is the dimension of the eigenspace, is essentially what it boils down to, or how many eigenvectors you have. That multiplicity of vectors per se, how many you have for that eigenvalue, is the geometric multiplicity. Where it is neither invertible or diagonalizable. Or diagonalizable. I don't want to like just come up with one off the top of my head. But it is possible, and you would just check that by doing um, I believe an example would be 1, 1, 1, 1. Your determinant is equal to 0, and you have m squared minus 2 lambda. No, that's a bad example. Yeah, I believe there exists some, but I can't come up with one off the top of my head, and I don't want to spend too much time uh, like dawdling on that. So if you want to email me, we can talk about that as well, or I can, if you want to look it up, that may be something worthwhile as well. Okay, if a matrix has, are there any other questions about this idea of algebraic geometric multiplicity and how to determine if it's invertible or diagonalizable? That's probably a good example. 0, 1, 0, 1, lambda equals 0, lambda equals 1, determinant equals 0. Yes. No. Yes. That's an example. Thank you, thank you, thank you. Okay. Cool little thought experiment to try and come up with one. 0, 1, 0, 0. So we have lambda equals 0, multiplicity of 2. Okay. Not invertible. Okay, because we have a lambda equals 0. And we know for a minus lambda I, which is just equal to a, there's one free variable, which means it has geometric multiplicity, oh, that is so bad writing, but whatever, of 1, 2, it's not equal 1, therefore non-diagonal. Cool, thank you for that. All right, so somebody else has asked, if a matrix has an eigenvalue with a multiplicity of 2 and 2 given eigenvectors, then it is not diagonalizable since the eigenvalues are not distinct. No, you can have a multiplicity of 2, but you just have to make sure that it has 2 eigenvectors as well, okay? Yeah, that's how that kind of translates. Does that make sense? Yeah. You just essentially have to check when you do a minus lambda I, count the free variables. If it is equal to the number of algebraic multiplicity you have for all of your lambda, if that is always equal, then it's diagonalizable, period, okay? If this had 2 free variables, it would be diagonalizable. Yes, yeah. If we had a zero matrix, right? 0, 0, 0, 0, right? This we have lambda equals 0, multiplicity of 2, okay? And it has 2 free variables, therefore diagonalizable. Yeah. I already talked about this matrix as well, I believe. Oh, no, I didn't, but yeah. Cool. All right, what other questions do y'all have? Anything about anything specific, particular? Okay. Quiz 7, question 5. I'll glance at that, and then I will explain stochastic matrices as well. Okay. Oof, y'all are already in quiz 7. Cool. Yeah. All right. So stochastic matrices. Actually, I'll talk about this one because it revolves around diagonalization in the quiz. And then I'll talk about stochastic matrices as has been asked. Cool. So, question asked. That is way bigger than I think. Okay. So here, find all values of A and B such that the following matrix is diagonalized. Cool. So right off the bat, what are our eigenvalues? Well, you plumb up the matrix. We have 1, we have 1, and we have 2. So lambda equals 1 with a multiplicity of 2, and 2, you can say it has a multiplicity of 1, okay? And again, these are algebraic multiplicities because they're numbers, right? They have no geometry to them. It's just the algebra. Okay, so we know 2 is a multiplicity of 1, okay? Therefore, we know it has 1 eigenvector. We don't, if we were to find like the CDC inverse breakdown of this, we would have to find that eigenvector, but it's just asking if it is diagonalizable, okay? So we don't really have to consider the 2 space here, okay? Does that make sense why we can skip that step? Anybody, if that doesn't make sense, we'll go ahead and say in the chat, let me know. Explain further. Okay, so we know 2 multiplicity of 1, right? We know that's an eigenvalue because it's diagonal, or because this matrix is triangular, right? There's our triangle. We know it has a multiplicity of 1 algebraically, and we know for each distinct eigenvalue, it must have at least 1 eigenvector, okay? So we already know that there exists some eigenvector for 2, okay? Right off the bat, we know that. Cool. Regardless of what B or A are, it's not going to change the fact that this is a diagonal matrix and 2 is on that diagonal, okay? Whatever A and B are, they don't affect the 2 part of this, okay? Does that part make sense? Like 2 is on the diagonal, period, cool. It's an eigenvalue. It'll never affect that. Since it only has a multiplicity of 1, it also at least has 1 eigenvector, okay? It has at least 1, but it can have any, I'll just go ahead and write this on a little sidebar. For varimetric multiplicities, okay? Your algebraic multiplicity is always greater than or equal to the geometric multiplicity, which is always greater than or equal to 1, okay? For any eigenvalue, all right? So in this case, we have an algebraic multiplicity of 1, okay? We know we have whatever that number is here, and we know it has to be greater than or equal to 1 as well. So we know it has to be 1, and 1 and the 1 are equal, therefore this satisfies our part of our condition for diagonalization, okay? So the 2 part we already know is set, okay? All of that just boils down to, because we know it's diagonal, and we know 2 sits on that diagonal, and it only happens once, we know it has an eigenvector, okay? So now we move on to the interesting parts. Interesting, but I mean the problematic part. 1 multiplicity of 2, okay? So we want our 1 eigenspace to be 2-dimensional, which is the same thing as saying 2 eigenvectors, which is the same thing as saying A minus lambda I, where lambda equals 1, has 2 free variables, which is the same thing as saying A minus lambda I, and the null space of that has dimension equal to, okay? All of these things boil down all of these things mean the same thing in this context, okay? And all of them, or any one of them, would satisfy this to be a diagonalization, for the one eigenspace to satisfy the condition for diagonalization, okay? So let's go ahead and look. We have 1, A, B, 0, 1, B, 0, 0, 2. Okay, pardon the background noise. Minus lambda I. Lambda is equal to 1, so this is just I. Okay, so this is equal to 0, A, B, 0, 0, B, 0, 0, 2. Okay, what do we want about this matrix? We want two free variables. Yeah, exactly, right? That's what it boils down to. We want two free variables. Yeah, so for this to have two free variables, we already have this one here. Check, that's 1, all right? Can this column ever be a free variable? No, that's not 2. Technically 1, but that doesn't really matter. Okay, never free. Okay, because we have that 1 at the bottom, and it's a pivot, right? So we know it's a pivot column, okay? So what we do want remaining is we want this to be a free variable. How do we make that a free variable? Why do we want two free variables? We want two free variables because we have an algebraic multiplicity of 2 for 1, and we want the geometric multiplicity to be the same so that so that we can diagonalize this matrix. Yeah. So in this case, we want this A to be equal to 0 so that we have 1, 2 free variables for this. Check. So that for each of our eigenvalues satisfies the condition for being diagonalizable. Okay. I know there's a lot of steps to this problem and a lot of quick walkarounds and stuff like that, but please ask those questions this time so we can talk through them and everything. Okay. Right. So, yeah, sorry, that was just an algebraic mistake on my part. It was 2 before. Any questions on this as a question? No? All right, fantastic. I'll move to number 4. And then I'll do stochastic matrices. All right, so consider the matrix A equals that. Obviously, based on just context and everything, this is C, D, C inverse, right? Does that make sense why we know that? Yeah, cool. So we know we have lambda equals -3. We know we have lambda equals 2, okay? So just looking at this, find C such that this is true. We know that we can go from 1 to -3 by multiplying by 3, -3, okay? So let's make this easy on ourselves and make this an eigenvector such that it's times -3 as well. That makes C equal to 3, okay? Any questions on this one? Cool, okay. All right, so stochastic matrices. Okay. One more note before we finally move to stochastic matrices. We can kind of block all this stuff together. Right. True or false? characters polynomial, blah, 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 then it's not invertible, okay? So let's go ahead and factor this to find out what our lambdas are. We can take a lambda out. Let's take a minus lambda out just to make our life a little easier. Lambda squared plus 2 lambda plus 1. So that's minus lambda, lambda plus 1 squared, okay? So from here we have lambda equals 0, and we have lambda equals -1. Since we have a lambda equal to 0, this is not invertible. That is true. Okay. For part B, the characteristic polynomial, just to like talk it over real quick, extremely quick thing there. Characteristic polynomial with a 3 by 3 of the 3 by 3 zero matrix is 0. No, it's lambda cubed. Okay. For any zero matrix, it's just that thing to the power. Okay. I'll get back to cofactor expansion and talking about eigenvalues and stuff. I probably should have started with that, but that's okay. We got time. Okay, so stochastic matrices. Oh, about number 5. Someone asked another question about that. B can be any real number because it doesn't affect our number of free variables for 1, and it doesn't affect whether or not 2 is an eigenvalue. Okay, so whatever it is, 2 will always be an eigenvalue, and it'll always have at least one eigenvector. And if A is 0, A minus 1I will always have 2 free variables, so B doesn't affect anything. So it can be whatever it wants. Okay. Just making sure nothing got buried in the chat. All right. Stochastic matrices. So basically, this is probability and linear algebra. Wow, so cool. All right, so I wasn't at last week's studio because I've been here, but I'm just going to explain everything regardless. So, stochastic matrices. A few things are always true, okay? They will always have a lambda equals 1. And it'll always be a line, okay? So that means it'll always have an geometric multiplicity of 1, okay? That's some theorem. I don't really know the proof for it, but that's just a fact to always know, and that's going to be important in a minute. Okay. Columns. Always. 2, 1. Always. Okay. Essentially, what a stochastic matrix is it's just a matrix of probabilities. Okay. So the way I like to think about it is this is our start up here. Start. Okay. And this is our end. Okay. So, I'll just call this an n by n matrix because it will always be square. All right. So each column is its own thing that we talk about. All right. So for this first column, we talk about things that are starting at position 1 is how you can kind of think about it. And then from there, what is the probability it ends or goes to 1 again? So let's say like they give you a diagram that looks something like this. Okay, 1, 2, 3. Have you guys seen these diagrams with the arrows and stuff before? Yes, no? Yeah, you have. Okay, cool. Let's say there's a 0.5 here, 1/4 there, and 1/4 there. Here, there is a 1/6 chance it goes there. There's a 1/3 chance it goes there, and a 1/2 chance it goes there. And for 3, it's going to happen when? Let's say 50% goes here, and 50% remains here. All right, so I'm just trying to fill out this, like these top 3 columns, okay? So, what is the probability that we start at 1 and end at 1? The probability is 0.5, okay? What is the probability we start at 1 and end at 2? The probability is 1/4, or 0.25, okay? And then the same thing for going to 3. The probability that we start at 1 and go to 3 is 1/4, also 0.25, okay? Probability that goes anywhere else is 0, because we know that it only goes to 1, 2, or 3, okay? That is why the sum always has to be 100%, because you can't have more than like what started there go to different places, and you can't have more people just kind of disappear and not make a decision, okay? So for the second column, we're starting at 2 and going to 1, okay? It is not starting at 2 and going to 2 in the first entry. It is starting at 2 and going to 1, all right? That probability is 1/3, so I'm just going to write 1/3 there. Probability that it stays at 2 is 1/6, and the probability that it goes to 3 is 1/2, okay? Those still all sum up to 1, so we know everything else is 0, okay? For 3, we know that 0.5 people start at 3 and go to 1. We know that 0% of the people start at 3 and go to 2, and we know that 50% go from 3 to 3, or stay at 3, okay? So we know that's there, and we know the resulting sum of the columns, or the resulting sum of the rows means nothing, okay? They can sum as high or as low as they want, all right? I mean, it always has to be at least 0, but cool. So that's just me talking about these first 3 entries and how to get that from a plot, all right? So that's how you kind of derive a stochastic matrix, right? Again, the whole idea is to model how things are moving, okay? It can model like, one of the big things that they talk about is the Google matrix. Google models what your preferences are going to be based on your history, and given weights of certain things, the probability that you do it. And the probability must always sum to 100%, which is just 1. So just like decimals and pretty basic probability, 0.5 is 50%, 0.25 is 25%, so on and so forth. Cool. So this is how we derive that from like a word problem or a diagram or anything like that. Okay. Any questions on that so far? Cool. Moving on. Let me pull this. 0.5, 0.25, 0.25, 1/3, 1/6, 1/2, 0.5, 0.5. Okay. Cool. Let's say I give you A equals this. Okay. A is a stochastic matrix equal to this matrix. All right. And I say, with the initial placement of people being 100, 0, and 50. Okay. So this is only important if we're doing a couple steps, okay? Not if we're doing like infinitely many, or where do things go as like we tend to infinity, or after a large amount of steps, anything that's equivalent to that. That's when we talk about our steady state vector, all right? Steady state vector, it is just our eigenvector for lambda equals 1, all right? And this is the probability that, I'll just say you'll end up there. I'm not going to get too technical and say like an element of the original, whatever, who cares? Okay, so if you have like 150 people, and like I'm not going to do the actual calculation of this, well, because we're about to go and do some calculations for eigenvalues and eigenvectors. But you would find that eigenvector, and let's say that vector is let's say it's 0.25, 0.15, 0.6. Okay. This is if you have 100 people, okay, 25 of them are going to end up in 1 every single time, 15 of them are going to end up in 2 every single time, and 60 are going to end up in 3 every single time, okay? And when you iterate again, people move in exactly the right proportion such that the same value stays in the same place, if that makes sense, okay? Like think if I have 200 people here and 200 people here, okay? And every time I do A, I tell 10 of them to walk over here and 10 of them to walk over here, right? Nothing really changes. We're at steady state, okay? After I do A, we're still 200, 200. We do it again, it's still 200, 200, all right? That's the idea of steady state. Cool. So in this particular case, for 1, if I have, well, I'll show you. Given like an initial thing here, like this vector, all right? We find the total number of things, and you just add up the entries for whatever your initial thing is. So that's 150 in this case, all right? And you just multiply total number by our eigen. For lambda equals 1. All right. So in this particular case, we had a total count of 150 people. So to see what the steady state looks like, all right, we're going to multiply 150 by 0.25, 0.15, and 0.6, right? Those aren't necessarily pretty numbers, but that's okay. That's 37.5, 0.2.5, and that's 90, okay? So essentially that boils down to, if I have that like same diagram I had up here, I'll just go back to it. Again, this isn't correct because I'm not going to spend the time. This is a general thing, so I don't know if the vector is pretty, so I don't want to spend like 15 minutes finding some crazy irrational eigenvector, but you shouldn't expect it to be anything particularly crazy. If I put 37.5 things here, if I put 22.5 things here, and I put 90 things here, each and every time I iterate or I do the things that these like branches and distributions say, things will move out just as much as they move in. So this is our steady state. Nothing changes, okay? When you guys get to differential equations, for those of you that have to take it, when you guys get differential equations, this is a huge thing for TVQs to help solve those. Isn't it supposed to be 1 over the total population? That's to get the distribution of things, okay? So like here, I made this like best case scenario where these sum to 1, all right? A lot of times you'll get a vector that looks like 25, 15, and 60, all right? And what you do in this case for your eigenvector is you need to make it stochastic, is the idea, right? You need to make it look like probabilities, okay? So for instance, like if I have 3 things and I give you 1, okay, my vector would look like 3 and 1, right? But you know that's the same thing as me having 75% and you having 25%, right? So that's why we go from our eigenvector to 1 over 25 plus 15 plus 60 times 25, 15, 60. Okay, this is for our one eigenvector. This is for our steady state stuff, okay? So this then gets us to the vector that we use, okay? Yeah, so essentially whatever our eigenvector is, we just want to make it stochastic, okay? Does that make sense? Are there questions about that? I know this is a tricky kind of like weird way to think about it, but please ask if you have questions. I want you all to do well on this as much as you do, so, well, probably not as much, but. Did you go over 3C in the text? Yeah, all right. All right, so now we move to the practice test. 6A on the practice test. Thank you for telling me that. That makes my life a little easier. Make sure that I have the right problem. 6A on the practice test. Cool. So yeah, we've talked about applications of eigenvectors and stuff, but may have skipped over the physical way to do that, but that is totally okay. It is essentially the same as taking the determinant, right? So let's talk about that. Taking the determinant. Why is that not working right? Okay. All right. The determinant of A. Cool. How we do it for anything bigger than a 2 by 2, okay? We'll talk it in two cases. We'll do a 2 by 2. A, B, C, D. Okay. For a 2 by 2, we just take this big diagonal and we subtract the little diagonal. Okay. So the determinant of a 2 by 2 is A D minus B C. Okay. Easy formula. That's the only thing that you really should memorize. Okay. For a bigger matrix, what we do is, the way I like to do it personally, is I put a plus in the top left, all right, just to start. I draw the matrix without any numbers. Okay, you guys can't really see that. All right, and then I move out and I go minus minus in the next tag. And this is a 3 by 3, so I should spread that out a little more. Okay, and then I move to the next diagonal. Okay, then I move to the next one, and then the last one. Okay, this is what happens when Dr. Chinkowski says you add up the or whatever professor you have adds up the indices of your entry, and if it is even, then it's positive. If it's odd, it's 0. Okay, so you can memorize this and be done, or you can think of it in a way for like this here, right? This has row of 1, column of 2, add them together, that's 3. It has a minus sign there, all right? That is important for when we do anything bigger than a 2 by 2 determinant, okay? So in this case, I'm just going to find the determinant first, and then we're going to do eigenvalues after that, okay? So have our 3, 0, negative 2, 0, 1, negative 2, 0, 0, 1. Okay, so we're going to walk through this, and I'm going to explain it along the way. Step 1 is to pick the prettiest row or column, okay? You usually want something with 1s, something that looks like easy, right? 1, 0, something pleasing, okay? Does anybody want to pick a row or column? I see 2 that are pretty easy, and either one of them are totally fine. Yeah, let's do row 3. That's totally fine. Okay. So row 3 in this case, how we do this is we take the entry, okay, and we multiply it by the determinant of this matrix, okay? We call that little one the minor, okay? So the determinant of this, and we're going to go by the third column. We don't have to specify that. And I'm going to write out each piece along the way just so we see it. We don't have to work it out, okay? So taking back to our matrix with pluses and minus, okay? For here, our 0 has a plus, so it's plus 0 determinant of its minor, and again, its minor is anything that's not in its same row or column, all right? So in this case, the determinant is 0, -2, 1, -2, okay? Cool. And now we move along the row or column we specified. So we move to the next entry, which is this 0 here, and it, looking on this matrix on the right, it is a negative, so it's -0, determinant of, where is it? Determinant of, so again, everything not in its row or column. It's a little confusing when it's broken up like this, but that's okay. 3, -2, 2, -2. Okay. Now we finish moving along the row. And here's where things are actually nice. So this last one has a plus. So it's +1 determinant of everything not in its row or column, which is 3, 0, 2, 1. Okay. Very obviously and intentionally, nope. This, 0. The second part is 0. The only part we care about is this part. Okay. So 1 determinant of 3, 0, 2, 1. And using our formula, that's just 1 times 3 times 1 minus 2 times 0, which is just equal to 1 times 3 or just 3, right? That's how we boil down and find that that's the determinant of our matrix, okay? Questions on this and how to take a determinant of something bigger than a 2 by 2. Cool. All right, move this to the side. Minor just means like the smaller matrix, okay? So for this case over here, right, the minor, so we had our 1 here, and our minor is everything without it, okay? So this is our minor, is what that's called, okay? Our minor matrix, essentially. And if it's a bigger matrix, like if it's a 4 by 4, these would be 3 by 3 matrices, and you have to do the same thing again, okay? But you still have to draw this each time, all right? Okay, so if you have a 4 by 4, obviously, you know, okay? Then when you do the determinant and you have your 3 by 3s, it's going to look like this, okay? It doesn't matter where the minor is placed, it's always going to come back to whatever the general shape means. Okay. Cool, cool. So, now onto the actual question. Come on. So, how do we find eigenvalues? Eigenvalues are the lambdas such that the determinant of a minus lambda I equals 0, which is the same as saying such that a minus lambda I has a free variable. At least one free variable, okay? And we call this long formula that we're going to arrive at the characteristic polynomial, okay? So a minus lambda I in this case is 3 minus lambda, 0, -2, 2, 1 minus lambda, -2, 0, 0, 1 minus lambda. Okay, following the exact same process we did last time, I'm going to skip a couple steps just to make our life a little bit easier, a little bit faster, okay? So we go through this bottom row, right? It's 0, right? Plus 0, whatever, minus 0, determinant of whatever, plus 1 minus lambda, determinant of its minor, which is everything not in the same row or column. 3 minus lambda, 0, 2, 1 minus lambda. Cool. So, what is the determinant Sorry about that. The experiment's dropping down, and they're opening up the radiation beam we're using. So, yeah, that's right. -1 raised to the power of the row and column is exactly the same thing as doing the plus minus matrix. I just like that because it's easier, and it does makes me think a little less, you know. So now we have 1 minus lambda, and the determinant of this matrix is 3 minus lambda, 1 minus lambda, minus 0 times 2, okay, which is 1 minus lambda, 3 minus lambda, 1 minus lambda, equals 0. And I'll simplify this to say 1 minus lambda squared, 3 minus lambda. All right. So now our eigenvalues are the zeros to this, okay? So when we go back to algebra, we have 1 minus lambda equals 0. Obviously, that's 1 equals lambda. And we have 3 minus lambda equals 0, which is the same thing as 3. Not 3 equals 3, technically, yeah, but 3 equals lambda, okay? So, eigenvalues, lambda equals 1, multiplicity of 2, because we have this lovely power here, okay? And lambda equals 3, okay? That's enough as is, or you can technically, if you want to get particular, multiplicity equals 1, multiplicity of 1, all right? Cool. That's how we find the eigenvalues for a 3 by 3 matrix. Are there any questions about this? Fantastic. All right, someone else asked for 3C on the practice exam. Okay, making sure that all these parts are not related. No, that was not what I wanted. Oh, no, that isn't. Sorry. All right. So C, T is a 2 by 2 transformation that reflects across the line. And let A be the standard matrix, which is the following matrix. So let's go ahead and construct this matrix. We're going from 2 to 2, reflecting across y equals -2x. Okay. So a couple ways to think about this. Let's do this geometrically. The way to do it geometrically is what happens to 1, 0 and what happens to 0, 1, right? When we reflect over, oh, right. So actually, we don't need to do that. These are more conceptual questions. So we'll talk about that at the. We'll derive A in class, just like an exercise. So this line is going to look like 1, -2, right? So for any reflection, only lambdas are 1 and -1. Always, 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 always. Okay. You see reflection, you should know right off the bat that the eigenvalues are 1 and -1. Okay. As a sidebar for something else that's relevant, for any projection, our lambdas are only 0, and 1. Okay. These are very important things. These are just you should just know these for the exam. Okay. If it's a reflection, lambdas are 1 and -1. If it's a projection, 0 and 1. Whatever their multiplicities are, it doesn't matter. However big the dimension is, like if you're in R4 and it's talking about a reflection across something, I'll talk about rotations as a little sidebar. Not as easy. But these are the two big things. 0 and 1 for projections, 1 and -1 for reflections. Yes, projections, 0, 1, reflections, 1 and -1. So the one eigenspace of a reflection is what is not being changed when we do it, right? So if we multiply AV and it's equal to V, okay? In this context, it means if we reflected about the line, nothing happens, which is equivalent to saying that we're just on the line, right? Because every time we flip across it, nothing happens, okay? So is the one eigenspace, or the space where nothing happens, equals to the span of this vector, which is just the line we're reflecting over? That is true, okay? Can it have more than two eigenvalues of 4 by 4? It will have more multiplicities, but it will only be lambda equals 1 and lambda equals -1. Okay. So, is it diagonalizable? Well, in this case, how many distinct eigenvalues do we have? 2. Okay. And how many eigenvectors do we need to make it diagonalizable? 2. So we know that it's there, and we know that that one is true as well. Because for each lambda, there is a eigenvector. Okay. So there's we have a multiplicity of 1 in both cases here, and they each have an eigenvector. So in all cases, our algebraic and geometric multiplicities are equal. All right. So this last question is the determinant of a plus I equal to 0? So this is the same thing as asking, is lambda equal -1 an eigenvalue? And we know that it is a reflection. So yes, true. Cool. Does that make sense? Can you go over part I again? Yes. So the one eigenspace of a reflection is what we're reflecting over, okay? One for reflection is okay, and the -1 also for a reflection is orthogonal to, I'll just call it, I'll say what we're reflecting over. Okay. Yeah. So in this case, the span of this line is our lambda equals -1 eigenspace. Okay. Because every time we reflect, it gets multiplied by -1. Okay. And talking about the one eigenspace, that it's just asking, this whole thing boils down to just, hey, is the span of this vector the same thing as the line we're reflecting over? And yes it is. Okay. Explaining part 3 again, it's just asking, is the determinant of a plus I equal to 0? Okay, well, if a plus I is equal to 0, that means a minus 1I is equal to 0. Okay, so this is the same thing as asking, is -1 an eigenvalue? Okay, and yes, it is, because it's a reflection. Okay, I is the identity. It's always the identity. And the one eigenspace is essentially the space that, like, when we multiply by a, it gets multiplied by 1. So if it's on that line, right? Let's say this is the line I'm reflecting over, and I have a vector here that points like this, okay? Every time I multiply by a or reflect over this, nothing happens to it. And if nothing happens to it, it's the same thing as multiplying by 1, okay? Cool. Any other questions on this one? This is a lot of conceptual stuff about eigenvalues and diagonalization stuff, so yeah.
If it said the -1 eigenspace of A is span 1, -2, that would be false.
That would be false because it is orthogonal to that space, all right? So it would have to be something like 2, 1, right? Because that's orthogonal to it, because now you guys know dot products and stuff, I believe, right? You guys know dot products? I don't think that's something you should be expected to do on an exam, but geometrically it's just what's orthogonal to it, or just perpendicular is another way to think about orthogonality. But yes, you're right. If I said the -1 eigenspace of A is equal to that, absolutely false. All right, someone asked for 7b. Okay. I always have to check on these multiple part problems if they're related or not. Okay. So A and B are 4x4 matrices, satisfying such that blah, 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 blah. Cool. All right. So determinant rules. Okay. Determinant of A is equal to the determinant of A transpose. Okay. The determinant of some number times A is equal to C to the n determinant of A. Okay. For each time you multiply a row by that amount, we multiply the determinant by that amount. And since it's inside the determinant thing, we just multiply it by the number of rows amount of times, which is C to the n. Okay. The determinant of two matrices A and B is just equal to the determinant of A times the determinant of B. Okay. And this is the same thing as saying the determinant of like A squared is equal to the determinant of A times the determinant of A, which is equal to the determinant of A. Okay. It just kind of comes out. All right. Cool. So in this one, it states determinant of A is equal to 5, and determinant of A B inverse, I should say, the last one is determinant of A inverse is 1 over determinant of A. Okay? These are your determinant rules. So, determinant of A B inverse, okay? So that's the same thing as determinant of A, determinant of B inverse equals 10. All right? So, determinant of A is given to be 5 times determinant of B inverse, which is 1 over determinant of A equals 10. So 1 over the determinant, that should be B. 1 over the determinant of B is equal to 2. Therefore, determinant of B equals 1/2. Okay? So now the question asks us to take it one step further and find the determinant of -2b. All right? Determinant of -2b is equal to -2 raised to the n, and n is given to be 4. Okay? times determinant of b. So that's equal to negative 2 to the fourth is 16. Determinant of b is 1/2. Therefore, this is equal to 8. Questions on this one? Why is n 4? N is 4 because it states in the question that it's a 4 by 4 matrix. All right, I saw something about 3C on the practice test. Did I already do that? No, I didn't. Oh, yes, I did. We did 3C. That was 7B. Now let's do 2D. Sounds good. If something got lost in the chat, I'm sorry. Just send it again and we'll figure it out. Cool. So this is a much more conceptual question, which they love to do. All right. So let's go through this. Suppose a is n by n, determinant is equal to 0. Determinant is equal to 0. What does that mean? It means we have a lambda equals 0. It means it's not invertible. And it means it has a null space. All three of those things are exactly equivalent in terms of matrices, square matrices. Okay. So for this one, dimension of the null space is greater than or equal to 1. Yes, because we know it has a null space because of these things here. Okay. The equation ax equals 0 has only the trivial solution. That is not true because it does have a null space, so there is a non-trivial solution for that. Saying we have a determinant equal to 0 is the exact same as saying we have at least a multiplicity of 1 of a lambda equals 0. So that's true as well. And the last one is the equation ax equals b must be inconsistent for at least one b in Rn. That must also be true because it's a square matrix and there's not a pivot everywhere. We know it's not 1-to-1, or we know it's not onto, so we can't get everywhere. So we know that that is true as well. Yeah, I know I went through that kind of fast, but please ask questions on those. There is kind of, yeah, which part? Or all of it?
One.
Okay. So the last one must be inconsistent for at least one b. Yes. Because if we have a lambda equals 0, we know we have a free variable. One free variable, which means a isn't onto, right? Because it's square, that means it's missing a pivot somewhere. So it can't span the whole space. So there's something missing, okay? So since we can't get everywhere, we know there's a b outside of the span. So it must be inconsistent for something. My pen is really light. Okay, yeah, sorry, let me change that. No, why did I miss the y? I'm going to post these notes as well with the recording. Yeah. Cool. How do we know it has a free variable? We know it has a free variable because saying determinant is equal to 0 is exactly equivalent to saying we know we have a lambda equals 0, we know it's not invertible, and we know it has a null space. All four of those statements are exactly equivalent for a square matrix. Okay? Cool. Any other questions on this one? I explained too. Yep. So this is a definition of null space. It has only the trivial solution, x equals 0. That is not true because if it has a null space, it has a non-trivial solution to x equals 0. That's what a null space is, right? Because again, a null space is just a times a vector equals 0. So if it has a null space, that means there's some v that isn't 0 to get us there. So it's non-trivial. Cool. for B. Okay. All right. So we know this is a diagonalization decomposition of A. All right. So I says that every non-zero vector in R2 is an eigenvector of A. That's not true. A way you can kind of think about that is if I have this, right, and I'm reflecting across this line, okay? If I have this, we can't describe it perfectly as multiplying by a constant as we reflect it, okay? That's not to say that we can't break it down into eigenvectors and then make it easy for ourselves, but it itself is not an eigenvector, okay? Because if we had this and we broke it down into, say, like the part that goes this way and a part that goes this way, like components of this other vector here, then we can multiply by A and make our life a little easier. But that doesn't mean it's an eigenvector, just because we can break it down into an eigenvector, okay? So that one is false. All right. Repeated multiplication of A pushes vectors towards the span of 2, 3. All right. So as we go to infinity, we have a lambda of 1/3. All right. So this part goes to 0. And we have an eigenvector of 1 times 2, 3. So yeah, you can think of that as kind of like a steady state kind of deal, right? For a lambda equals 1, that's what we tend to as we go to infinity, of multiplying by A that many times, okay? That's true. 3, if negative 1, 1, then an approaches the 0 vector as n becomes very large. That is true because that is within the span of this vector, all right, corresponding to this eigenvalue, all right? So anx is equivalent to saying negative 1/3 raised to the n times negative 1, 1. Okay? So obviously, as n gets very big, that just goes to 0. So that's true as well. And IV, those two being eigenvalues, that's true. 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 Oh my god. Cool. Questions on this one? Are there any other questions about anything before we break for the night? I'm going to go over and end the recording, and I'm going to talk about rotations. That's outside of the scope of something like to easily derive, but it's just a fun little whatever. 2b. Yep. That's another important one. We'll do that one real quick. And somebody asked for explain 2 and 3. Do we need to know other definitions besides 2a? That's really just like the big one, right? For an eigenvalue, not particularly. Everything else is more helpful, but that's the only one you really need to like nail in and know. Okay, so question 2b. And for going over 2 and 3 again, 2 and 3, this one, because as it, multiplying a to infinity happens, the 1/3 part goes to 0, and whatever component that lies close to 2, 3, that remains, because it's just being by that like component, if we break it up, it's just being multiplied by 1 every time, so that's what we kind of tend to. Okay. That's a little bit of a high concept, but nothing too far out of pocket. And the last one is just saying that, hey, this is an eigenvector corresponding to lambda equals 1/3. As we go to infinity, what happens? It just crumbles away and goes to 0. So, going over this one, all right. There are other rules. Now here, row swap. determinant times -1, row multiply determinant times that number, okay? I can go into detail about something like, where did it go? Yeah, about why this doesn't matter, okay? That's a little bit of a long explanation. Essentially, oh, it's not too long. I'll go over it real quick. So essentially how it works is I go from A, B, C, D, and I multiply -4, or I'm actually going to swap rows first. So I'm going to do D, E, F, A, B, C, G, H, I, okay? All right, so just to go through why that doesn't happen at all right? So we go from here to D, E, F, -4A, -4B, -4C, G, H, I, okay? And now we combine those two rows, and adding rows does nothing, okay? So this one is -1 times the determinant. This one is times -4, and then we add, we get -4A plus D. Nothing happens here. And then to go back to resolve our middle row to make it easy to get it to its final form again, -4A plus D, -4B plus E, -4C plus F, okay? A, B, C, G, H, I. And we multiply this time by -1/4, okay? So it's easy to see that this and this cancel out, all right? So you can just kind of boil it down to this rule of regardless of what the row that you're adding is multiplied by, nothing changes, okay? Cool, that's how that works. So, so going back to the actual question, all we're essentially doing here, we are swapping rows, that's multiplying by -1. We're adding rows, that does nothing. 0 the line through it is nothing. And that is all. So we multiply our original determinant, 3 times -1. So that gets us -3. And that's our final determinant. Cool. Any questions on this? They don't often go through this derivation of like why that doesn't matter, but I hope that makes sense, that you can see it, and it makes things a little bit more clear for you.
Thank you.
Yeah, absolutely. All right. So I am going to end the recording, but I'm going to talk about complex eigenvalues and eigenvectors just as as an aside of what they mean, okay, which may help the understanding of it. Actually, I'll leave the recording on, but yeah, the scene of like questions and everything. Yeah, scaling a row changes the determinant. That's what this rule here says. If you multiply a row determinant, you just multiply the determinant by that number. So, any other questions before we go? Cool. So complex eigenvalues. Okay, essentially what they boil down to is if you have a number like √2/2 plus √2/2i, all right? What this boils down to is this has a scalar component and it has a rotation component, all right? And the rotation component corresponds to some like if this is your real, this is your imaginary, okay? This angle is your rotation component, and the scalar is how long this part is, right? So for this particular one, the scalar is ×1, and the rotation is 45 degrees, all right? So for something that's rotating 45 degrees, we'll have √2/2 plus or minus root 2 over 2i, okay? Plus or minus in all cases, all right? I know that's not super intuitive, but this is what complex eigenvalues actually mean. Complex numbers basically boil down to I not meaning anything, and we're just trying to keep the parts of a number separate. We're keeping the real part over here, and we're keeping a different part over here, all right? So having the change there means that we have a rotation, all right? That's when we have a rotation, we have complex eigenvalues. If we don't, and it's all scalars for eigenvalues, then they're all explicitly real, okay? But as soon as you have a rotation, you're going to have complex eigenvalues, okay? This is a really neat thing. It comes up a lot in electrical engineering and a lot of different things like that, mixing signals and talking about all kinds of different stuff like that. You don't need to know like exactly that's how it works, and that's like why we just can snap to those things or like whatever. Like for example, in a different example, like if we had like root 2 plus root 2i, all right? This now has a scalar of times 2 and a rotation of 45 degrees, okay? So that's this idea and the whole like thing that people don't talk about for some reason, which doesn't make any sense to me, about what like complex numbers actually mean. And as an engineer, this is going to be a pretty big thing that most of you are going to see a lot. So it's very important to note that it's just distinguishing two parts of a number, okay? It's signifying some kind of rotation or a phase shift or an out of phase component or whatever, or some kind of y component and x component. It's totally dependent on the thing, but yeah. Okay, so the way that we do the scalar, technically, it's just the magnitude of the two numbers, okay? So it's actually, no, it's, that's, okay, that's a bad example. It wouldn't be 2, it'd be 2 root 2, because the magnitude is the square root of 2, no, it is 2. Of root 2 squared plus root 2 squared, which is equal to the square root of 4, which is equal to 2. So that's our scalar component. It's our magnitude of the two parts, okay? I will send an announcement about my office hours tomorrow. Again, I'm at JPL doing like radiation experiments, so my availability is kind of odd, but I will do my best to have an online office hours. I'll send out the link as that happens. I'm just going to be like periodically busy throughout the day doing research stuff, so I'll send an announcement sometime tomorrow about it. Yes, so that's how we get the scalar component. The rotation component technically is arctangent. I know, arctangent, absolutely horrifying, of the imaginary part over real part. Again, if this is going way over your head and you're confusing yourself, don't mind it. Just like move past it. That's totally okay. I'm not asking, you're never going to ask you to like derive this based on this, like whatever. Like, okay, like this is just like some big picture conceptualizing of what it is to help you actually understand what's going on when you have a complex eigenvalue. Because looking at that for the first time, like what the fuck does that mean, you know? Cool. Any questions about anything else? What's the question they'd ask? That's to do with complex. They'd ask you to find something that has a complex eigenvalue and eigenvector at best. They wouldn't ask you like what it, like, here's a complex eigenvalue. What rotation does it pertain to? They're not going to ask you anything like that. Yeah, cool. So I'm going to stop the recording.